Hello everyone. My name is Rahul Kumar Prasad. I am a student from BSc third semester and the topic for my assignment is Davisson and Germer Experiment for Diffraction. Coming to the introduction, the Davisson-Germer experiment was a 1923 to 1927 experiment done by Clinton Davisson and Lester Germer, an astonishing duo of scientists at Western Electric, later Bell Labs, in which electrons scattered by the surface of a crystal of nickel metal displayed a diffraction pattern. This confirmed the hypothesis advanced by Louis de Broglie in 1924 of wave-particle duality and was proved to be an experimental milestone in the creation of quantum mechanics, and this experiment further led to be the foundation for quantum mechanics. Now, talking about the history and overview of the experiment, we come to know that according to Maxwell's equation, in the late 19th century, light was thought to consist of waves of electromagnetic fields, and matter was thought to consist of localized particles. However, this was challenged in Albert Einstein's 1905 paper on the photoelectric effect, which described light as discrete and localized quanta of energy, which is now known as photons. And these findings won him the Nobel Prize in Physics in 1921. In 1924, Louis de Broglie presented his thesis concerning the wave-particle duality theory, which proposed the idea that all matter displays the wave-particle duality of photons. According to de Broglie, for all matter and for all radiation alike, the energy E of the particle was related to the frequency of its associative wave, nu, by the Planck relation E equals to h into nu, and the momentum of the particle was related to its wavelength by what is now known as de Broglie's relation, as we can see in the figure as lambda equals to h by mv, where lambda is wavelength in meters, v is the velocity in meters per second, m is the mass in kilograms, and h here is Planck's constant, in which is in the unit of joule per hertz. Now, an important contribution to the Davisson and Germer experiment was made by Walter M. Althusser in Göttingen in the 1920s, who remarked that the wave-like nature of matter might be investigated by electron scattering experiments on the crystalline solids, just as the wave-like nature of X-rays had been confirmed through X-ray scattering experiments on crystalline solids. This suggestion of Althusser was then communicated by his senior colleague and the later Nobel Prize recipient Max Born to physicists in England. When the Davisson and Germer experiments was performed, the result of the experiment was explained by Althusser's proposition. However, the initial intention of the Davisson and Germer experiment was not to confirm the de Broglie hypothesis, but rather to study the surface of nickel. Now, talking about the early experiments performed by Davisson and Germer. Davisson began work in 1921 to study electron bombardment and secondary electron emissions. A series of experiments continued through 1925. Prior to 1923, Davisson had been working with Charles H. Kunzman on detecting the effects of electron bombardment on tungsten when they noticed that 1% of the electrons bounced straight back from the electron gun in elastic scattering. This small but unexpected result led Davisson to theorize that he could examine the electron configuration of the atom in an analogous manner to how the Rutherford alpha particle scattering had examined the nucleus. They changed to a high vacuum and used nickel along with various other metals with unimpressive results. October 1924, when Germer joined the experiment, Davison's actual objective was to study the surface of a piece of nickel by directing a beam of electrons at the surface and observing how many electrons bounced off at various angles. They expected that because of the small size of electrons, even the smoothest crystal surface would be too rough and thus the electron beam would experience diffused reflection. Experiment consisted of firing an electron beam from an electron gun and electron particle accelerator at a nickel crystal perpendicular to the surface of the crystal, and measuring how the number of reflected electrons varied as the angle between the detector and the nickel surface varied. The electron gun was a heated tungsten filament that released thermally excited electrons, which were accelerated through an electron potential difference, giving them a certain amount of kinetic energy towards the nickel crystal. To avoid collisions of the electron with other atoms on their way toward the surface, the experiment was conducted in a vacuum chamber. To measure the number of electrons that were scattered at different angles, a Faraday cage or Faraday cup electron detector that could be moved on an arc path about the crystal was used. The detector was designed to accept only elastically scattered electrons. Now, during the experiment, air accidentally entered the chamber, producing an oxide film on the nickel surface. To remove the oxide, Davisson and Germer heated the specimen in a high temperature oven. Not knowing this caused the formerly polycrystalline structure of the nickel to form large single crystal areas with crystal planes continuous over the width of the electron beam. When they started the experiment again and the electrons hit the surface, they were scattered by nickel atoms in the crystal plane, so the atoms were regularly spaced of the crystal. This, in 1925, generated a diffraction pattern with unexpected and uncorrelated peaks due to the heating causing a 10 crystal faceted area. They changed the experiment to a single crystal and started again. Now, talking about the breakthrough of the experiment, Davison attended the Oxford meeting of the British Association for the Advancement of Science in summer 1926. At this meeting, he learned of the recent advances in quantum mechanics. To Davison's surprise, Max Born gave a lecture that used the uncorrelated diffraction curves from Davison's 1923 research on platinum with Kunzman, using the data as confirmation of the de Broglie's hypothesis, of which Davison was unaware of. Davison then learned that in the prior years, other scientists like Walter Alsasser, E. Z. Diamond, and Blackett, James Chadwick, and Charles Ellis had attempted similar diffraction experiments, but were unable to generate low enough vacuums or detect the low intensity beams needed. Returning to the United States, Davison made modifications to the tube design and detector mounting, adding azimuth in addition to colatitude. Following experiments generated a strong signal peak at 65 volt and an angle theta equals to 45 degree. He published a note to Nature titled The Scattering of Electrons by a Single Crystal of Nickel. Questions still needed to be answered and experimentation continued through 1927 because Davison was now familiar with the de Broglie's formula and had designed the test to see if any effect could be discerned for a changed electron wavelength. According to de Broglie's relationship, which they knew should create a peak at 78 volt and not 65 volt as their paper had shown, because of their failure to correlate with the de Broglie formula, their paper introduced an ad hoc contraction factor of 0.7, which however could not explain 8 of the 13 beams. By varying the applied voltage to the electron gun, the maximum intensity of electrons diffracted by the atomic surface was found at different angles. The highest intensity was observed at an angle theta, which was equals to 50 degree, with a voltage of 54 volt, giving the electrons a kinetic energy of 54 electron volt. As Max Born law proved in 1912, the periodic crystal structure serves as a type of three-dimensional diffraction grating. The angles of maximum reflection are given by Bragg's condition for constructive interference from an array, where Bragg's law can be given as n into lambda equals to 2d sine 90 minus theta by 2 for n equals to 1, theta equals to 50 degree, and for the spacing of crystalline planes of nickel where d equals to 0.091 nanometer obtained from previous X-ray scattering experiments on crystalline nickel. According to the de Broglie relation, electrons with kinetic energy of 54 electron volt have a wavelength of 0.167 nanometer. The experimental outcome was 0.165 nanometer via Bragg's law, which closely matched the predictions. As Davisson and Germer state in their 1928 follow-up paper to the Nobel Prize-winning paper, these results, including the failure of data to satisfy the Bragg's formula, are in accord with those previously obtained in our experiments on electron diffraction. The reflection data failed to satisfy the Bragg relation for the same reason that the electron diffraction beams fail to coincide with law beam analogues. However, they add the calculated wave lengths are in excellent agreement with the theoretical values of h by mv, as shown in the accompanying table. So, although the electron energy diffraction does not follow Bragg's law, it does come from de Broglie's theory that particles behave like waves. However, the experiments did not follow the de Broglie calculation, which lead to attempts by Carl Leckett, A. L. Patterson, and Fritz Zwitz to make an examination of de Broglie's calculated electron wavelength by the contraction factor or index of contraction. Davisson and Germer accidental discovery of the diffraction of electrons was the first direct evidence confirming the de Broglie hypothesis that particles can have wave properties as well. Davisson's attention to detail, his resources for conducting basic research, the expertise of colleagues, and luck of all contributed to the experimental success. Now, talking about the experiment, in 1927, at Bell Labs, Clinton Davisson and Lester Germer fired slow-moving electrons at a crystalline nickel target. The angular dependence of the reflected electron intensity was measured and was determined to have the same diffraction pattern as those predicted by Bragg for X-rays. At the same very time, George Paget Thomson independently demonstrated the same effect, firing electrons through metal films to produce a diffraction pattern. And Davisson and Thomson shared the Nobel Prize in Physics in 1937. The Davisson-Germer experiment confirmed the de Broglie's hypothesis that matter has wave-like behavior. This, in combination with the Compton effect discovered by Arthur Compton, who won the Nobel Prize in Physics in 1927, established the wave-particle duality hypothesis, which was a fundamental step for quantum theory and quantum mechanics. Now, we see the experimental setup of the Davisson and Germer experiment, where we can see we have a vacuum chamber where it has a heated filament which accelerates the electron beam. We have an accelerating anode there, and electron beam is coming through the heated filament, which falls on the nickel target, making an angle with the movable detector. Now, talking about the experimental arrangement of Davisson-Germer experiment, we have an electron gun comprising a tungsten filament F was coated with barium oxide and heated through a low voltage power supply. While applying suitable potential difference from a high voltage power supply, the electron gun emits electrons which were again accelerated to a particular velocity. In a cylinder perforated with fine holes along its axis, these emitted electrons were made to pass through it through producing a fine collimated beam. The beam produced from the cylinder is again made to fall on the surface of a nickel crystal. Due to this, the electrons scatter in various directions. The beam of electrons produced has a certain amount of intensity, which is measured by the electron detector, and after it is connected to a sensitive galvanometer to record the current, it is then moved on a circular scale. By moving the detector on a circular scale at different positions, that is, changing the theta angle between the incident and the scattered electron beams, the intensity of the scattered electron beam is measured for different values of angle of scattering. Now, talking about the observations of the experiment, we get the following observations. We obtain the variation of intensity L of the scattered electrons by changing the angle of scattering theta. By changing the accelerating potential difference, the accelerated voltage was varied from 44 volt to 68 volt, with the intensity L of the scattered electron of an accelerating voltage of 54 volt at a scattering angle of 50 degree. We could see a strong peak in the intensity. This peak was the result of constructive interference of the electrons scattered from different layers of the regularly spaced atoms of the crystals. With the help of electron diffraction, the wavelength of matter waves was calculated to be 0.165 nanometer. Now, talking about the practical applications of the Davisson-Germer experiment, it wasn't until the 1960s that vacuum tubes were adequately made reliable and available to expand on the electron diffraction technique. But since that time, scientists have used LED diffraction to explore the surfaces of crystalline elements and spacing between atoms. I would like to thank my physics faculty for giving me such a wonderful assignment as I came to learn many things from this assignment. Thank you.